Hello, this is the next video on quadratic forms. And in a previous video, we looked at quadratic forms corresponding to diagonal matrices. And diagonal matrices are a very special type of symmetric matrix. And it's easy to see what kind of quadratic form you get. It's just going to be, well, for a quadratic form in two variables, it's just going to be ax squared plus by squared. And we saw that we got different graphs of z equals ax squared plus by squared. So we saw that if you have a function z equals ax squared plus by squared, if a and b are both positive, then you get this bowl-like shape like this. And if a and b are both negative, then, so here's the graph of z equals ax squared plus by squared. The graph is gonna be a bowl, but like this. And if one of a and b are negative, so if a is positive and b is negative, or a is negative and b is positive, then basically when you take one cross-section, you're going to get an upward pointing parabola, and when you take another cross-section, you're going to get a downward pointing parabola. And what ends up happening is you end up getting some Pringle-like shape where on one side it's like this, and then on the other side it's like this. And you get this Pringle-like shape. It's like a saddle, something like this, and then like, I used to be good at drawing these, but it's kind of hard to visualize, maybe like this. Okay, let me try one more time. It's going to look like, this is where technology can be really useful. Actually, this picture might be the better one. It's this kind of shape like this. Oh yeah, this is looking better. It's this weird shape that looks like a Pringle chip. Okay, and the point 0, 0 in the first case is a minimum, and in the second case 0, 0 is a maximum. In this case 0, 0 is what's called a saddle point. And in this video, so this time, what we want to look at is what happens if you have a more general symmetric matrix. So what if you have a more general symmetric matrix that is not diagonal? All right, let's look at an example. So let's say that you have this matrix, and this is a matrix that we talked about in a previous video. So it's this matrix. Well, what's the associated quadratic form of this matrix? If you do z equals xy times a times xy as a column, this is going to equal this matrix xy times the vector x plus root 6y, and then root 6x plus 2y. And this is going to be x squared plus 2 root 6xy plus 2y squared. And the question is, when you graph this, what do you get? So if you wanted to graph this function, z equals this, what does the graph look like? Well, the problem with this is that it's hard to graph. It's hard to figure out what to do to graph this function. So it's hard to graph and visualize when the function is written like this. And to get a better handle on what the graph of this is, we can work with the matrix A. Do you remember what fact we have? How is A related to a diagonal matrix? It's an orthogonal matrix times a diagonal matrix times an orthogonal matrix. Right? That's the spectral theorem for a symmetric matrix. And what we're going to do is we're going to relate A to the diagonal matrix lambda. That's a diagonal matrix. And we're going to use that to figure out how to like re-express this function that's hard to graph. And then we'll be able to see how to graph it. So to see how that works, we need to write A in the form Q lambda Q inverse. And fortunately, we did that in a previous video. We saw that A is equal to root 6 over 15, 3 over root 6 over root 15, 3 over root 15, root 6 over root 10, negative 2 over root 10. That's our matrix Q. And then lambda was 4, negative 1. And then we had Q inverse, which is the same as Q transpose. Well, our function z was equal to this matrix times A times this matrix. And since A is Q lambda Q transpose, it's this times Q times lambda times Q transpose times this. So in this case, z is equal to xy times, now let's see if I can save some time and just, let's see, can I copy this? Yeah. Z is equal to this. Oops, okay. Let me move this a bit here, times xy, right? Now notice that this is the same, this part, when you transpose it, you get this. So let's just multiply those out. Z is equal to root 6 over root 15x plus 3 over root 15y. So that's the first component. And then root 6 over root 10x minus 2 over root 10y. So it's this times this matrix 4, negative 1 times the transpose of what we had here. Root 6 over root 15x plus 3 over root 15y, root 6 over root 10x minus 2 over root 10y. Now, what we're going to do is we're going to define new variables. See, this looks very complicated, but notice how much simpler this matrix in the middle is. It's a diagonal matrix. And we can take advantage of this by defining new variables, two new variables. We started out with x and y, but let's define u and v. Let's define u to be this one and v to be that. Okay. Well, if you do that, then we see that z is equal to uv times this diagonal matrix, lambda, times uv. We can express the function z, instead of in terms of x and y, we can express in terms of u and v. And this is going to be 4u squared minus v squared. So let's think about what's going on in terms of the graph. So originally, we have the x and y axes here, and that gives you this xy plane, and then you have the z-axis, like this. And with that, you get the graph of this function that's hard to visualize. But now what we're going to work with is a different set of axes. We have the u-axis and the v-axis. And the u-axis is going to be like, well, u is equal to some combination of x and y. And so it's going to be like, I don't know, maybe like this. So here's the u-axis, and then the v-axis is going to be orthogonal to the u-axis. And so now we can say, well, what happens if you use the u and the v axes instead of the x and y axes? So if you use the u axis like this and the v axis like this, we still keep the z axis, but we're graphing using the x and instead of using the x and y axes, you're using the u and v axes. And it's 4u squared minus v squared. So when u is 0, you get z is negative v squared, and when v is 0, you get z equals 4u squared. So when u is 0, z is negative v squared, and so you're going to get this downward, let's see, on the zv plane, it's this parabola like this. And on the zu plane, it's 4u squared, so you're going to get this. And so the graph of this function is this odd shape, and the point 0, 0 is a saddle point. So do you see how we used the spectral theorem to figure that out? Originally, we had some complicated function, f of xy equals x squared plus 2 root 6 xy plus 2y squared. Hard to figure out what's going on there. But since we used the spectral theorem, And we came up with new variables, u and v. So we wrote v like this. And when we defined u and v to be using this, we saw that we can just write z as 4u squared minus v squared. And using these two new variables, okay, these new axes, since z is some simple thing, 4u squared minus v squared, we can see that the graph is going to be such that 0, 0 is a saddle point. And what's going on is that the eigenvalues here, we have one eigenvalue that's positive and one negative eigenvalue. If we had, instead of for negative 1, if we had something like for positive 1, then your z in terms of u and v is going to be 4u squared plus v squared, and then it's going to be a bowl that's upward pointing. It's kind of, right? And then if you had negative 4 and negative 1, then you're going to get negative 4u squared minus v squared, and then you're going to get an upside down bowl. So what did we learn in this video? We saw that when you don't have a symmetric matrix that's diagonal, like in this matrix, it's not diagonal, it's still symmetric, we can diagonalize the matrix. Okay, we knew that from the spectral theorem, but the point is that we can use that diagonalization to understand the associated quadratic form. We can use the diagonalization to come up with new variables u and v. Okay, you define u and v by taking the matrix Q inverse. So this matrix was Q inverse or Q transpose. Q inverse and multiplying it by the vector xy, and that gives you your new u and v. So, that you can use, and when you do that, you're going to get, well, the point is that you have this diagonal matrix lambda here, right? This was a diagonal matrix. And so you end up going back to where you were before, where you had something of the form a u squared plus b v squared. And depending on the values of a and b, those are the eigenvalues, right? Lambda 1 u squared plus lambda 2 u squared. Maybe I'll just write it down like that. Lambda 1 u squared plus lambda 2 u squared plus lambda 2 v squared. Once you have that, you can use whether the eigenvalues are positive or negative to determine what the shape is going to look like. So if lambda 1 and lambda 2 are positive, you get this paraboloid that's kind of pointing up. And then if you have negative eigenvalues, you get this upside down bowl. And in this example, you had one positive eigenvalue, one negative eigenvalue. You got this, the graph is this shape where 0, 0 is a saddle point. And this is something that is used in multivariable calculus. So in the next video, we're going to talk about some quick ways to tell whether your symmetric matrix has positive eigenvalues or negative eigenvalues, or, you know, some that are positive and some that are negative. And that will make it easy to tell what shape we're going to get. Thanks for watching.